Okay, so what I actually wanted to do today is in a way to wrap up this kind of deep learning part. I had some kind of loose ideas of talking about principal component analysis and unsupervised learning, but I decided more to defer that to later, and then rather try to wrap up the thing which deals with the recurrent neural network, which some of you may actually encounter in your actual research. There is additional material on what's normally called generalized adversarial networks, which some of you may be interested in. And then one of the plans we have after we've basically been done with project number 2 is to start to look at Bayesian optimization. And that's a field which is very, how to say, I'd say that many people actually, when it comes to machine learning and or statistical learning, which is perhaps a better word, that tends to move into the field of Bayesian machine learning, Bayesian optimization, Bayesian Gaussian processes of things which many of you may have heard of, and which many of you will encounter in your actual research. I don't know how many of you are going into a more kind of machine learning approach in your research. So at least 1, 2, and 3. And the kind of statistical learning is, we thought actually because we have Anders Kvellestad, who you actually haven't met that much. He does research on Bayesian processes. And the thing which I'd say is beneficial from that point of view, if you look at what we have been doing till now, is that we put less emphasis on the extraction of a probability distribution, which describes the data, the parameters which we have. It means that it's more difficult to make a proper error estimates of the parameters which we have. So like when we did linear regression, we could actually find a confidence interval for the parameters. But we have been very sloppy or a little bit laissez-faire with the underlying statistical interpretation. Now, the powerful thing with Bayesian statistics, so Bayesian statistics and standard machine learning, it's a kind of, previously people would say that they were pretty distinct, but now many of these concepts are just floating over to one field and to the other one. But traditional machine learning has more dealt with what we call a frequentist approach, where you take the data you have and you use that to infer a probability distribution. The Bayesian approach is a little bit different because you assume that your data follows a specific distribution. And then you try to find the distribution given some specific conditions. So if you have X, what is the probability that that leads to Y? Given an initial guess for the probability of X and Y. So that means that you have more kind of belief in a specific probability. But then the field of Bayesian statistics has really exploded in the last 2 decades. And you have things like Bayesian model averaging, Bayesian optimization, and many, many other subfields. So that means that when we often do science, we are equally interested in finding correlations in the data and making a prediction, which we have been doing in machine learning now. But we also want to make an estimate of the errors. And we want to have a deeper understanding of causations. So if I have X, what is the probability of getting Y given X? And these are often things which are treated in a more laissez-faire way in traditional machine learning. So like what we have been looking at in the last weeks with convolutional networks is very much this: you train your data, you train everything on a huge data set, like a huge set of images, and then you want to classify new images based on a pre-trained data set. So there is a data set like ImageNet, which we discussed previously, which contains millions and millions of images. Some of these images are actually controversial. So like on face recognition, there was a long tradition where you actually wanted to recognize criminal faces and to actually say something about criminal behavior by taking mugshots of people who were jailed, right? And these kind of images have actually entered this huge data set on face recognition. You have had other projects from especially the US Army where they wanted to say something about your facial expression and connect that with emotions of people. Now, and this is pretty bad actually, because there's no scientific foundation for that kind of connection. But it led actually to people being stopped at airports because you were sweating, probably because you had flight anxiety. So there are many small controversial things which are important to keep in mind. We are a little bit fortunate because we do science, and then we have more, how to say, scientific problems where these methods are relevant for us. And it's not uncommon that you could train a huge data set in convolutional networks on specific experimental outputs. So like in my field, which is nuclear physics, we have tons of events which often have lots of noise. And then we can pre-train a convolutional neural network on a model for the experimental data, so what we expect to see, without noise. And then we can use that as a pre-trained network and then analyze the data with noise. So that's something which clearly sounds like it's been disconnected from, let's say, face recognition algorithms, but much of the same mathematics and underlying methods can be used for that as well. So we haven't dealt so much with some of these ethical consequences, but also because we are more into science problems, but it's something to come. One of the things I wanted to talk about is a little bit about recurrent neural networks. And if you go into the slides here, you will find, again, some of these resources on videos on recurrent neural networks. There's a general one on deep learning. And also this textbook by Goodfellow et al. This is written by some of the experts in deep learning. And I'd say it's perhaps to date one of the better ones when it comes to giving you a kind of bird's view of what the different methods stand for and what they contain. If we look at what we did last week and the week before about convolutional neural networks, this is a way to reduce the dimensionality of a problem by filtering specific features. So compared with a standard deep neural network where you actually treat dense matrices and dense vectors and perform matrix vectors, matrix multiplication, you're now actually filtering some specific features through the mathematical process of convolution. And as we saw last time, there were different types of operations. So we had the convolutional process, so the convolution itself, the filtering, and then you sent this through some activation function, and then you could have this pooling where the max pooling was a standard one in order to further reduce the dimensionality. So these different stages here, they would normally be called the convolutional stage or the convolutional layer, but then you could take this layer and add new convolutional layer and further reduce it, or just train a standard deep neural network. Now, when we now come to recurrent neural networks, the thing is that the recurrent neural networks, they are in a way back to what we did with standard neural networks. And they are normally memory intensive, and they are CPU intensive. And some of them, the standard setup is also difficult to parallelize. So there are some pros and cons, which we are going to discuss throughout the lecture. The thing is that if we now look at, let's say, feed-forward neural networks and CNNs, they do not normally perform well on data. Actually, they do not perform well on data with unknown length. And this is where recurrent neural network actually become interesting for us. So what happened here? Yeah, I think I clicked on another window here. So our focus has been on convolutional networks and feed forward, but then the output of the activation function flow only in one direction. And from the input layer typically to the output layer. A recurrent neural network is like a feed forward, except that it also has connections pointing backward. And you can have at each step you can have an external input. So it means that a typical setup for or data setup, which is relevant for a recurrent neural network, would be something like a time series. And some of you will probably deal with time series in your PhDs, which means that you will collect, for instance, experimental input at given time steps. You may have some kind of external input to the system that produces an output at a given time. And then you move on to the next time and you repeat the experimental setup with a new input. And then you get a new output. And this propagates through time. And you would typically then like to make a prediction. How does this propagate beyond the time for which you have data? So that means that you could take a limited set of experimental input, train your network on that as a time series, and then make predictions on how the system will behave at later time stages. That would be a typical situation which I would encounter in my own research when I solve time-dependent differential equations. So that's a typical situation. And people have actually used these recurrent neural networks for solving or studying time-dependent differential equations. But it's also used to analyze things like stock prices and tell you when to buy or sell. In autonomous driving systems, these are actually used, recurrent neural networks. They can also take sentences and documents or audio samples as input and making them, and that makes the recurrent neural network extremely useful for what normally called natural language processing, such as automatic translation and speech to text. So many of the machine learning algorithms are for language recognition actually based on recurrent neural networks. So it's a interesting application. And I guess that some of you may actually deal with time series in your PhDs. Does that ring a bell? Somebody who's been already looking at time-dependent data? So recurrent neural network will typically be one of the methods one could use there. So I just wanted to give you a very simple example first of what we can do with these recurrent neural networks. So let me just bring up this example. So this example here, I'm using now TensorFlow to build up a recurrent neural network. And what I'm simply doing now is to set up a array of data which contain just a sine function, as you can see here. So this is sine. And in the first run, what I could do now is just to take away this and take away the noise and just run it without noise. So what I'm doing now is something extremely simple. I'm producing 1,000 data entries of sine functions. That's not very exciting. And what I'm going to do then is to train my recurrent neural network on the first 800 points. And then I'm going to make a prediction on the remaining 200 points. So as you can see here, what I've done here is to say that my data set is equal to 1,000, and the training points is the first 800. And then I'm setting up a recurrent neural network. So I have my train X and train Y. I'm just converting everything to a matrix. In using TensorFlow, I need to define this as a sequential network. I set up a very simple one, which has 32 units. I'm coming back to what these units are. I use the ReLU as an activation function. I add a final dense layer. And then my error here is the mean squared error because I'm parameterizing a function. And then I simply do the fitting of the model, training and everything. And so when I run this code, what you would see then is something like this. So this is my sine function, which I'm plotting. So not very exciting, up to 1,000 points. This gives me now the parameters which are trained. So this is a pretty shallow network. It's not very deep. And then if you then look at the, let's just scroll down here a little bit. And then you can see the quality of the result. The loss function is getting better and better. And there should be an image here. Sometimes I have to screen. So we should see an image at the end here. There we have. So you can now see the blue line is the original data. The orange line is the prediction I make with the network, or the first 800 points are used to fit the model. And then I have my blue line, which you can see here, and also the orange line. So what you see from beyond this red bar here till 1,000, this is actually the prediction I'm making, where I just trained everything in the first 800 points. So you see how you can use a recurrent. This is a very simple case, but you could have experimental data which are given at different time steps. And then you could train the recurrent neural network on the first 800 data which you have, and then make a prediction for later data points. So this is a typical example of how you can use recurrent neural networks. Now, if you were to add more noise here, then clearly you would see that. So you see the loss function is pretty, so this is actually the error you make as you move on. So it's getting smaller and smaller, which is also pretty satisfactory. So you're typically on the third decimal point. If we now change this one and add some noise here, so let's do that. So here we are. So depending on the size of the noise here, so we could do that one and just rerun everything. Now your data these are the original data, so they are actually much more noisy. And that clearly is going to give you a poorer cost function, which is the mean squared error in this particular case. So if you now look at the values you get, you see now that your error is not at the third decimal point. So it's actually around 0.3. So it doesn't seem to be diminishing either. And if you look at the final image here, you will see something like this, where the orange one is the prediction you make. So it follows this sine shape, but it's struggling a little bit more with the reproduction of the data set. So when you have lots of noise, it clearly is making it much more challenging to reproduce the pattern here. So this is just something to keep in mind. But you see the kind of power of these recurrent neural networks. And the typical situation is that you would train on some data and then make predictions on the behavior of the data. So what I actually wanted to do is to go through some of the basic setups and how you construct a recurrent neural network. And that will wrap up the discussions which we have had about deep learning methods. And then we could, at the end of the second lecture, we could discuss a little bit about possible paths for the last part. We can also tailor things more to your own specific needs. So in case what we are suggesting is not that interesting for all of you. Okay, so I'm going to change to the whiteboard. So let me just do that. So if you look at the typical situation which you may encounter in RNNs, that is the solution of a differential equation, a time-dependent differential equation, and a famous time-dependent differential equation. Let's take a look at that one, a time-dependent ODE as an example, just to get started. And then one of the classical ones is that of harmonic oscillation. So you could have something like Newton's equation of motion here with the acceleration. You could have some damping term. So this would be a velocity dependent term. And then you could have some plus x of t. And then you have some applied external force. So that's a very common situation which I encounter in scientific simulations of physical systems. This could also, it doesn't need, if you look at the left-hand side, it doesn't need to be a Newtonian-like system. This is a typical set of equations which you would encounter if you're studying harmonic oscillations, where you have some damping. So the first term is your acceleration times the mass, which is the force acting. So all these are the forces on the left-hand side. And the type of equation when you solve these equations is that you would normally discretize the solution of them, and you would have some kind of solver. And that could be as simple as the Euler method. So you would typically, if you now use Euler's method, But this is just an example as a kind of warm-up to the way we are going to label the various elements in a recurrent neural network. So if you discretize, we know that we have x of I plus 1. The next time step is given by some x of I plus some time step delta t times the v of I. And v of I is nothing but the derivative of x of dt at x equal to this discretized point x of I. And then if we look at the velocity, what we would have then, if we take the differential equation dv dt, because we know that dv is given by this term here. So the acceleration is given by the derivative of the velocity. This is now given, if we now look at these parameters which we have, it's going to have a minus an eta, and then dx dt is the same as the velocity, and then we have a minus, and if we divide by m, so this should have a divided by m, divided by m, an x of t, and this is equal or plus an f, we just write this better, plus an f of t divided by m. And what we could say now is the following, is that what you see here is something which we could now rewrite in terms of some complicated function. So we could now simply say then when we are updating things is that we have a v of I plus 1 is equal to the previous value v of I plus delta t, and now we have the derivative of v of I. And we could now say that this is given by some function f, which now includes all these complications which we have here. And this function is now going to depend on the velocity at this position, at this time step. This force f of I is going to depend on x of I, and it would also depend on time step t of I. So what I've done simply is just collect all these terms which represent the derivative for the velocity in terms of a function f, which now includes all these terms here. So there is a dependence on the velocity at a given position of this specific force on time and x of I. Now, the reason why I do that is that I'm going to rewrite this in terms of kind of more general types of operations. But what we could say is that if you look at what we have here, if we now take away this previous v of I, we could actually rewrite this now in terms of the function f, if this doesn't change from step to step. So the mathematical function little f now contains all these variables. And what we would have then would be something which would depend on f at the previous time step. So that would be v of I minus 1. It would contain this f of I minus 1, x of I minus 1, and t of I. So that would actually be my velocity here, which I have here. So that, and then it would in addition depend on the force at f of I, x of I, and this t of I. So you could have this kind of repetitive set of operations. So this is the kind of keyword, the repetition of the operation. So the dynamical structure of the time evolution is now encoded in this kind of repetitive mathematical operation. So this is a, just writing it down, this is a repetitive set of operations. Now, what I'm going to do now is simply to simplify things a little bit. And I'm going to let this v of I plus 1 now, instead of having this complicated function, I'm simply going to let this be represented by some object s of I plus 1, which now includes all these kinds of quantities. So this S of I, let me just call it like that, is going to be given by a function H. And this will contain information from the previous step. There is a generic variable X of I. And then we have some parameters, theta. So these theta are going now to be the parameters of the network, because I want to rewrite this in terms of a specific network. So what I'm doing now is, instead of taking this expression here, which has this repetitive feature, I'm now just going to encode this in a slightly simpler way. And you will see now that these H's are going now to represent different types of hidden layers. That's why I put this naming H on them. Now, there's one thing which is very useful when you're setting up these things, and that is to look at what's normally called computational graphs. So let's take a quick look at that. So that's a tool which we're going to use now. And if you look at these computational graphs here, so let me just show you some examples. So this is pretty common to use these in the setup of recurrent neural networks and convolutional neural networks. So if you look at the operation set is equal to X times Y, the way you would typically write it would be something like X here, you have your Y here, and these confer through the process of multiplication. So you would typically write an X here to indicate that this is a multiplication, and then you would have a final Z here. So that's a way to represent that mathematical operation. If you think back to a neural network, we had something like Y, which was given by an activation function. And then we had X transpose times the weight matrix plus a bias, B. And normally that was something which we wrote as an F of Z. So Z was given by this quantity here. And if you write as a computational graph, the way you would actually put that up would be something like X, and then you have the input to Z here, and you have your W, which is set up in terms of your weights. So you would have a dot operation between the vector and the matrix, a vector matrix multiplication. And then this would now add, you would add the biases. No, sorry, you would add this into the function F. Let me just rewrite that one. So this goes into the function F. And there you also input the biases which you have. And this would give you the final result, which is Y. So this is another way of actually writing down the mathematical operation which we put up in a standard neural network. So these kind of computational graphs are very much used in the setup of these kind of operations. So one way you would now, if we now go back to what you have here. So what I did was to replace V with some general object S of I. So I actually should have written this as changing V to some general object S, which we haven't specified. And that is given in terms of some specific functions H here. So if you want to make a graph of that one, what you would typically see then would be something, if we now go back, so let me just look at my cheat sheet here. So what you could have is something like an initial position, initial state here that produces an input to this function S of I at the time I minus 1. This can also get an input at the stage xi minus 1. So this is now an input to the system at a given time step. We may produce an output or we may not produce an output. But you could think of a simple thing like this. So you update this S of I. You have a new input here, X of I. This continues now till the final time step, S of I plus 1, with a new input, X of I plus 1. And this goes on all the way to a final time step here. So you begin at a given time step or initial time, and you have a final time at which it ends. So if you now are setting up the specific network which we are going to look at, a recurrent neural network, the first sketch of a recurrent neural network could be something like this. So you have initialized your hidden layer, something like this. You have some H0, and this feeds in to an H1. And you have some input here, some X1, and this produces an output, some Y1, and then this continues, so you have a new box, H2, and you have an X2 here, and you produce a new output, Y2, and this goes on as long as you are doing measurements. Now, the way you can think of these now would be something it's a figure like this when you're setting it up. So your H's are now supposed to be the your hidden layers, where you do much of the fitting of the weights and the biases and so on. So the way you can think of setting up a recurrent neural network in more detail. So let's try to do that and bring in some more space here. So what we could do then is that we have some output which we have measured at a given time step. So you have an initial situation here, and this feeds in to a specific H here. So and this H is a function which now represents the hidden layers. And we take this at a time t minus 1. This feeds into, so when we are wrapping up the details, into a function f, where the input of the weights go into this function. This receives now a input from some external, this could be some external probe we have. It could be this force which we apply to the system at a given time. Then you feed in from the previous layer the weights which you have into this function f together with the input. This produces now an output from your model. So just keep in mind the difference here. So we now produce an output of y of t tilde. And then we're going to plug this in to a loss function or cost function. So I'm just writing this as c of t, so that's the cost function. And into that one, we're going to make a comparison with the data. So y of t is the data which results from a measurement made at a time t. Then, when you're done with that, so this function f, that actually produces an input to the hidden layers h of t at the time t, and that is the one which conspires to produce this function. So it shouldn't be like that. Sorry, I should take that one away. This is now connected to the next time step, f. It receives a new input from some external force which we have, or some engine which is acting on the system. And then this feeds now into the next h of t plus 1, which then goes in and produces a new output from the model. So what we are doing now is actually to make a model for the output tilde, y tilde, and we want to compare that one with the measurement which we have. So at every time step, you could say that the so-called kind of experimental data or your observations, they are given by x here, and then your y of t plus 1, which you have here. So this should be plus 1, plus 1. So these are the data which you have at each time step. So what you see in between is the model you are making to describe the data. And now the question comes, how do we train this model to reproduce the data points which we have at each time step? And this can be done in many different ways. The most standard way you train a recurrent neural network is that you have this type of connections from a hidden layer in here. It produces the activation functions. It has the activation functions. It produces an output from this, which is now fed into the calculation of this y of t. So what you could have now is that this one sends to an output layer. So typically this one, what you see here, that would be normally what we call the output layer. This h of t doesn't need to be one hidden layer. It could be many hidden layers. You could also have a mix of convolutional layers and normal feed-forward neural networks. So you can actually make these H's, which you see here, these ones, you can make them as deep as you want. But clearly, the deeper you make them, the more CPU intensive it becomes, and the more memory intensive it becomes, because when you're training this network, you're actually keeping the values of the weights. So the more time steps you have, and the deeper you make the network at each time step, the more you need to store. So you could treat these as kinds of these h of t's here as either shallow or deep neural networks or convolution neural networks. So if you want to now look a little bit more into this, and you now want to look at the parameters which you have. So let's try to look at the way we are going to train such a network. So let's look at the parameters and try to label them. So at each step now, so you have from ancient times, you have something like an H here. So that is your hidden layer at the beginning. So I'm just leaving this unspecified. This transfer a set of weights, which now go in to the hidden layer at a time t minus 1. So the previous hidden layers are connected with new ones, and that's where you have the history. So when I trained this sine function, what I was actually using then was my sine function from the previous time steps, and that will be fed in to the next time step, and it will be connected with weights. So when you're training now, you need to store these weights. Then what you have, you don't need to have an input at each time step. But normally when you run an experiment, you have some kind of way to influence the system. You may make some experiment with some input. For instance, you're measuring the voltage or the way neurons fire, you send in a signal, and that will be the signal you send in at that specific time step. And at that specific time step, you also have an observation. So that means that when you now look at this x of t minus 1, which is your external probe, which could simply be a signal you send into your brain cells and see how the neurons fire. Then this is also connected in your model. It has a set of weights, which are represented by this variable u, so which needs to be trained. Because keep in mind that what is between the output and the input from an experiment is your model. So everything we are making up here is actually parts of a model here. Now, these hidden layers, they then produce an output. And so this will be, when you think of a neural network, this will be the connection between your neural network, the last hidden layer, which we call the output layer, which then produces the output. So here you need also some weights, and there will be biases as well. And that means that we have some y of t, that's the output from the network. This feeds in to the cost function at that specific time, c of t minus 1. And that's where we compare with the observations which we have. Now this feeds in again to the next time step. So this is actually how we build up the memory of the system. And then we have a u here, we have an x of t, and then this feeds up. So this v here, that is the connection between the hidden layers and the output, which is then fed into the cost function again. So c of t, and then we have the y of t, and this clearly just continues till a final time step here, a final time. So if you now look at, so for each step now, with you actually have a forward propagation. So you need to initialize it. So for each time step, there is a forward propagation. From the initial time. So we received an input from a previous time step, from the initial time to the final time, towards the final time. So the what you need then is a kind of following. If you look at the different weights, so the weights are now sending in an input to a set of activation functions. So you would have something like the following quantities you need at a given time step. You need something like a z of t, which then enters an activation function in the hidden layers. And you can have many such hidden layers. So just keep that in mind. So you can make these as deep as you want. So what you would have then would be something like a set of t, which has a bias, as before. And then I would have something like this w, these weights. And this is multiplied now with the output from the previous time step. So this has an h of t minus 1. So previously what we had was the output from a previous layer, in a hidden layer, in a feed-forward neural network. Now the quantity which we're going to use now is actually the output from a previous hidden layer, and that is fed into the next time step. So this is again how we build up the memory here. And then what we need as well is this matrix U of x multiplied with x at the time t. So what you have there would now be the this part here, this external application to your system, which then affects your system and produces an output. And then this feeds in with W and U, and they produce an output, which will be your H of t. And this H of t then is actually this function Z goes into, so that means that H of t then, that will be given by some function which takes this Z of t. So we need that. Now, what happens next is that the y of y tilde at the time t is now given by a new function, which we call g. So that could be another type of activation function. So if we're dealing with a classification problem, that could be a softmax function. If we are dealing with a fitting problem of a specific function, or what we normally call a recursion problem, then we end up with something like the mean squared error, or similar types of functions. So this would now involve this h of t multiplied with this matrix V, which contains the weights, plus some new bias. And G could be a function like the softmax or other functions which are relevant. So this G, if you have a classification problem with many different types of classes, so we could then say that G could be a softmax function. Just to give you an example here. And so forth. So there are many types of functions which you can set up depending on your type of problem. And the same applies also to the hidden layers which you have. So I see that we are past the hour. So I'm going to stop here. Pause the recording. So this network here, which we have, has, I mean, it's very powerful, but it has several drawbacks. So let me just point to the drawbacks. And then we can look at another way of setting up, which is very popular, by setting up a so-called recurrent neural network. So the drawbacks in this specific case here. So when you're computing the gradients, I'm just going to write this down here. So computing the gradients. Of this specific, of the functions which we have, because we are calculating the gradients of the cost function. Functions means that with respect to the parameters which we have, with respect to the parameters, and these are the parameters of the functions or the matrices V, W, and U, and the biases. It's a pretty expensive operation. Maybe we could lock the door there, because then lock the door, because I'll close the door because we get the noise from the. Oh yeah, I forgot that. Yes. So computationally, this is an expensive operation, and normally what we need is a forward pass from the left to the right. And then when we're done with the forward pass, we actually have this is then followed by a back propagation. And this is normally, this leads to something which is called the back propagation through time. So it's called BPTT. So that's called the back propagation. And that's how we train these different weight matrices. Back propagation through time. People have shown that these networks are pretty powerful in reproducing data for time series. But one of the other drawbacks here is that it's almost impossible to parallelize it, because when you typically run a parallelization, you would like to see, let's say, different time steps as something which has separate units, and then you could parallelize each time step with respect to the time steps. But now the input to the next time step is given by the information which you have for the previous one. So this is a very sequential setup. And that means that it's normally often difficult to parallelize. So what you could do then is that you could replace this kind of feed forward from the hidden layer by simply using the output from the previous layer. So one of the recipes which is used is to replace the link between the hidden layers with just the output from the previous layer. From previous layer. And that leads to another type of architecture, which is also much used. It's easier to train, but it lacks the kind of hidden-to-hidden connectivity, which has been one of the strengths of the recurrent neural networks. So one of the reasons why recurrent neural networks have become a little bit less popular is due to the fact that they are CPU intensive to train and memory intensive, because you need to keep all the weights in memory when you're training your network. So the typical way you would do that is, suppose now you have some previous output. So let's just write it like this with dots in here. And this feeds in to this hidden layer, HT-1. This has the input from a kind of external engine or a specific input to the system. And then you produce a new output, y of t-1 tilde. This is then fed into a cost function, c of t-1. And that receives also the observation which we have, or the target, which is also another name for it. We would then have the same matrices, V and W, or the same type of weights and biases which are needed in the connection between the input to the hidden layer. But then what happens now is that we would use this output from the previous layer as an input to the next layer. So we would have only this one which enters this specific quantity. And then we would have a U here again. We would have an X of T, and then this will produce a new output, Y of T tilde, which feeds into a cost function, where we then again compare with the observation which we have. And this would just continue. So the weights which we had previously, which connected the hidden layers, are now weights which just connect the output with the next hidden layer. So we would have the output here, which then feeds into an HT plus 1, and so on. Just putting dots here just to indicate that this is just a very repetitive structure here. So people often oscillate between these two types of network setups. Normally, this one has been less used because it gives often a worse reproduction of the data. We have something which is called long short-term memory setup of networks for these recurrent neural networks. So there are many different ways of modeling this kind of recurrent neural networks. So if this is something which is of interest for your own research, I mean, there's a lot of interest in literature which you can look up. So in these lectures, I just wanted to guide you to the basic principles of the different types of either convolutional neural networks, recurrent neural networks, and so on, so that you get a kind of a bird's view of the essential features of these types of networks. Now, there is one problem with these networks here, and that's the problem of so-called exploding gradients or vanishing gradients. That becomes even more important here, because now we are taking this weights which we have here, and they are being propagated through the whole network. And that can easily lead to a problem with the training if the gradients become too large. And there are normally some brute force approaches which are used in order to avoid that. And one of the most used methods is called the gradient clipping. So if it becomes too large, you simply reduce it. So let's look a little bit of what may happen. So recurrent neural networks, they suffer even more from what we discussed in the beginning about the exploding or vanishing gradients in the training. So let's take a quick look at that, and then just try to conclude what we have here. Now, one thing I wanted to say also is that you can see now, if you go back to the previous network, the standard recurrent neural network, what you need then is actually to calculate pretty many gradients. So you need the gradients of, if you look at the expressions you have, you would need the gradients with respect to these parameters. So for the cost function, you need these gradients. You need the gradients with respect to the biases. You need the gradients with respect to this quantity. You also need the gradient with respect to V and C. So your parameters are now hidden in here, 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 and here. So that clearly also complicates the calculation of gradients. And it's very easy that the gradients can run amok, create serious problems in the training. So one of the things which one tries to avoid them, if you now look at the suppose we just take the, suppose now that the weights are the same throughout the whole network. So one thing which we are doing then is that we are computing now, if we take away the biases. So let's look a little bit closer at this problem with exploding or vanishing gradients. And what we have is something like an h of t, so which now would be the function which depends on the output from the previous layer. So suppose now that we just model the new output in terms of the weights times the output from the previous layer, and we take away the biases. And we have taken away an activation function. Let's just assume that this is what takes place. So normally what you would have had would be something like an activation function, where you have this function z of t, and where this z of t would now be given by w of h of t minus 1 plus the weight b. And in this case, we also have this u times x of t in order to complicate life. But let's now assume that the weight function for this activation function just produces the output by the multiplication of a matrix with the previous output from the previous time step. This is just a simplification, just to illustrate how we can analyze the problem. So that means that what we would have then, if we look at this h of t, we would now have, if we do this t time steps, this will be given by the application of this weight matrix, which we now assume is the same throughout the network. And then we have multiplied with the initial output from the hidden layer. So one of the things, if we now can find the eigenvalues, so assume that lambda I is an eigenvalue of this matrix W. Eigenvalue of W. And then we could now expand this H0 in terms of these eigenvalues, so eigenvectors. So we would have an alpha I, which is just a constant, multiplied with the eigenvector. So this would be an eigenvector. So I'm just making a very simple model now in order to see how the system can develop without taking into account the complication of an activation function in every single layer. So when we repeat this t times, we know that when I act with w times h0, this is the same now as I of alpha I of lambda I of wi. And if you repeat this a certain amount of times, so repeat t times, then what we have is wt times h0, which is this h of t. So this becomes simply now, since we're acting on the same with the same matrix on the same eigenvectors, we get an alpha I of lambda I to the power of t multiplied with the eigenvectors. Now what you could assume now is that this matrix is now ordered in terms of a descending series of eigenvectors. So these are ordered so that lambda 0 is the largest one, lambda 2, and so on down to lambda of n. And then we assume that this matrix is a real matrix of dimensionality n times n. Now, if that is the case, we see very clearly that if this lambda 0 is larger than 1, then these kind of functions will diverge. So we will then get an h of t, which just keeps growing. So then h of t will grow. And it will finally lead to exploding gradients. And if lambda 0 is less than 1, then h of t will clearly, as t just increases, will just start vanishing, will diminish. And this normally leads to the problem of vanishing gradients. Now, this analysis is very simplistic, as you can see, but it tells you what kind of problems you can encounter when you train this type of networks. Because these weights, they feed in to the next layer, to the next layer, to the next layer. And since you repeat this many, many times, you can encounter a situation where actually the gradients, it's not unlikely that the gradients will explode or can vanish in the training. Yeah.
Does this generalize to imaginary eigenvalues?
If you have imaginary, normally the weights are assumed to be real. So you assume that the matrix is linked to real eigenvectors and values.
But real matrices can't have imaginary.
They can't. But we're assuming that the eigenvectors are real. So that's a normal assumption you make about this, but they could actually have. That's correct. And also in this specific case, this is an assumption I've made to simplify my analysis.
Yeah.
So this is not given, right? Because your matrix doesn't need to be symmetric either. So here I made the assumption that they have a symmetric matrix, just to simplify the mathematics. And also to take away some of the complications, I also now assume that my output is not modulated through an activation function. Because the normal situation is that you choose an activation function like a Rayleigh function or similar ones, and you feed the input through that one in order to produce a new output h of t. So what I said now is that the output from the hidden layer is just given by the previous layer's output multiplied with the weight function. And then I simplify the problem, assuming that this is a matrix with a real eigenvalue. So one of the cases which, and you can see that clearly there's a type of matrices which will not give us problems. So if the eigenvalue is 1, the largest eigenvalue, you know what kind of matrices these are, right? Anyone remembers that? What's the name of a matrix which has the largest eigenvalue equal to 1 that belongs to a specific class of matrices? In particular, if you can sum either one of the columns or one of the rows to 1, that's normalized to 1. Stochastic matrix. So a stochastic matrix has a largest eigenvalue equal to 1. And that's the essence in a random walk. If you do a Markov chain and you have and you propagate a Markov chain, you're assuming that you have stochastic matrices which represent the transition probability to a new situation. They have the largest eigenvalue equal to 1 if the Markov chain converges to a steady state. If it doesn't converge to a steady state, that means that you don't have a proper stochastic matrix. So for this specific, this very, very simple example I took to illustrate the problem, then the ideal here would be to have a fully stochastic matrix. That may not be the case when you're setting up your weight matrices because you're doing a complicated training. So view this as a very idealized situation, which may not correspond to reality. And since you normally know that you can encounter this type of problems, there is a recipe, a standard recipe for avoiding the exploding gradients. So the standard recipe, I just wanted to mention that. So it's very ad hoc for avoiding exploding gradients. That's normally called gradient clipping, and some of you may have heard of that. And the way you would do that here is simply to say the following. If your norm 2 of the gradient, so G is now the gradient, is larger than a specific value, epsilon, which you have set, then what you do then is that G takes a smaller value where you take this epsilon divided by the norm of G to multiply with G. So you just replace the gradient with a new value, which is then meant to avoid this exploding gradient. So you just reset the value to a maximum value. And that's NDIF. It's as simple as that. So I'd say that this kind of vanishing gradients is actually the vanishing gradient case is another type of problems which you can encounter. And what you would normally do then is to tune the weights and the biases so that you can avoid it. And you would do that in much the same way as you would treat a feed-forward neural network, where we discussed the vanishing gradient problem. We're setting the weights accordingly to a normal distributed set of weights. That's a standard way of dealing with the vanishing gradients. For the exploding gradients, which is not unlikely that it happens, and specifically since we are repeating these operations again and again through time, then the gradient clipping is a standard recipe which is applied. It doesn't sound very satisfactory, and to me it is not, but that's the kind of practical recipe which people do. So I'm just trying to see it because I know there was something else. There's something else I wanted to say there, but now my memory is failing me. Yeah, there are some other kind of small tricks of the trade which are being used also in order to reduce the memory needs and the number of CPU cycles, is that you train the weights for the different matrices for a given time, and then you just stop training them and you use them for the rest of the time steps. So that's also kind of recipe which has been used in these kind of methods. So this actually concludes what I wanted to say about the deep learning methods. I'm going to just stop the recording. In the slides, you will find more information